Polarisation and intermolecular forces. A polar molecule is a molecule where one side of the molecule carries a charge that isn't balanced out. So usually one side of the molecule is delta positive and the other side is delta negative. If the molecule is asymmetrical and this doesn't balance out, it creates a permanent dipole. An example of a polar molecule is water. The hydrogen atoms are delta positive whilst the oxygen is delta negative. Water molecules are attracted to each other as a result of this. On a flat surface like glass, this attraction can be seen between water molecules as water beads up. Sulfur dioxide is a polar molecule because of the difference in electronegativity between sulfur and oxygen, and again, this isn't balanced out, creating a permanent dipole. A temporary dipole moment is where electrons in an atom may be asymmetrically distributed at any kind of moment. These electrons are constantly moving around, so these temporary dipole moments are constantly being created and destroyed. But the overall effect is that atoms are attracted to each other. A permanent dipole-dipole force is the weakest kind of intermolecular force other than temporary dipole-dipole forces, and that they arise between permanently polar molecules. So these forces exist between the delta positive and delta negative ends of two different polar molecules. Hydrogen chloride is an example of a molecule with a permanent dipole. In contrast to the hydrogen atom, which has a partially positive charge, the chlorine atom has a partially negative charge. The positive hydrogen of two hydrogen chloride molecules attracts the negative chloride of the other when two hydrogen chloride molecules are brought close to one another, creating a bond. Hydrogen fluoride is another example of a compound with permanent dipole-dipole forces, and this happens in the same way as hydrogen chloride. Water has hydrogen bonds. Hydrogen bonds are the strongest type of intermolecular force that take a lot of energy to break. This means that water has a very high melting point, boiling point, and specific heat capacity. Water also has permanent dipole-dipole forces since water is a polar molecule, as I said before. In order of decreasing strength, the types of intermolecular bonds in water are hydrogen bonds, which is the strongest, permanent dipole-dipole forces, and the temporary dipole-dipole forces, otherwise called van der Waals forces. Each water molecule has the ability to create 4 hydrogen bonds, 2 with its own hydrogen atoms and 2 with the hydrogen atoms of other water molecules. When water freezes to make ice, water makes 4 hydrogen bonds in ice, whereas when it's liquid water, it's only an average of 3.4 hydrogen bonds. These extra bonds means that each water molecule is held further away from each other, making ice less dense than water. This is a very good property for water to have, as it means when ponds and lakes freeze over, only the top freezes and the ice floats, meaning that sea creatures can survive underneath in winter. Water has a very high specific heat capacity. 4.186 joules of energy is required to heat a gram of water by 1 degree. In comparison to air, this means that it holds on to heat for a long time. The specific heat capacity means that water isn't subject to very quick temperature changes. So water is at a stable temperature so that sea creatures can have an averagely sort of stable environment, which is another good property of water so that creatures can survive in it. Water also has a high heat of vaporization, meaning the amount of energy required to convert 1 gram of a liquid substance into gas at a constant temperature is high for water. The specific heat capacity is also linked to melting and boiling points of water. These will have high values, like I said before, due to the hydrogen bonds. The specific heat capacity is always infinite at the melting and boiling point, since the substance's temperature remains roughly consistent as it undergoes a phase change but still requires a certain amount of energy. The boiling point of water is 100 degrees Celsius and the melting point is 0 degrees Celsius. Atomic weights of elements may be determined using the periodic table, and we can look at elements' molar mass. So in the absence of other intermolecular forces, the higher the molar mass, typically the higher the melting and boiling points. This is because usually if an atom has higher molar mass, it means that there are more bonds to destroy, which takes higher energy. However, water has high melting and boiling points because of its hydrogen bonds, despite having a relatively low molar mass.